Okay, welcome to the walking talking mock for triple physics. So we're going to start with the first question, which is question 2. The table shows the half-life and penetration power of some isotopes A to E. We can see they've got a range of half-lives. So half-life is the time taken for the activity to decrease by half. Now, it says activity. We could also say the number of radioactive nuclei. We could also say the mass of radioactive isotope, or we could say the number of decays per second. So there are a few ways we can define half-life. And then the penetration power. So how much can it get through? So penetration means pass through. So it says a medical tracer is injected into the body for medical imaging purposes. A medical tracer contains a radioactive isotope that emits radiation. This radiation is detected from outside the body to produce an image. So this is the person. There is a detector around them. The radiation is inside. They will drink it in a drink, and then the radiation is emitted and it is detected, and then you can trace back from where it's detected to see exactly what's going on inside the body. So evaluate which isotope will be best suited to use as a medical tracer. So evaluate means gives the positives, and it means give the drawbacks as well. And if we just look at the number of marks, it is 6 marks. So we've got to write quite a lot for this. And then there's one further bit of guidance. Use your knowledge of the risks and benefits of using radioactive isotopes for medical imaging in your answer. So there's a few things that we are going to talk about. We'll talk about the half-life, we'll talk about the penetration power, we'll talk about the risks, we'll talk about the benefits. So that's 4 things straight away we can talk about, and hopefully that will give us at least 6 points. So it's always worth doing this in an exam on a 6 marker, highlighting the kind of things you want to talk about, and then you can tick them off when you've done them. So let's look at the half-life. So a medical tracer needs a kind of medium half-life. Now that on its own is a bit vague. Medium doesn't really mean anything. So let's explain that. So 5 years or 47 days is too long. So A and E, the half-life is too long. Alright, because the radiation would remain in the body for too long, causing damage for a long period of time. So the radiation will remain in the body, causing damage for too long. Okay, so we don't want this one, we don't want this one. Let's have a look at these ones. 5 hours, 2 minutes, 6 hours. Well, 2 minutes, C, 2 minutes is too short to carry out the tests. Okay, if you drink something with the radiation in 2 minutes, half of it will have gone, 4 minutes, 3/4 will have gone, and so on. So by the time you get into the room with the detector, it's probably all gone. So that's no good. So now we're down to B and D. So B and D, suitable half-life. Okay, because after about a day, almost all of the radiation will have gone from the body. So let's have a look. D, now for the penetration power, reduced by thick lead, and B, stopped by thin aluminium. So B is unlikely to be useful, as thin aluminium and so likely a human body will block most of it. I'm not saying it's impossible that this one is used, but it's unlikely this one will be used because a body will stop the majority of this radiation, which means very little can be detected. So a human body will block most of it, leaving very little to be detected. Whereas D can pass out of the body and be detected. So we've talked about half-life, we've talked about penetrating power, we've said D is the most likely isotope. What else do we need to do? Well, we need to use our knowledge of the risks and benefits of using radioactive isotopes for medical imaging. So we should probably just talk a little bit about the risks and benefits. So the risks, radiation is ionizing. It mutates DNA, leading to cell death and increased cancer risk. So we need to link this to what we've already said before in order to get top marks. So A, E, or D, these will give you the highest dose of radiation. Alright, because we've already said A and E will be inside your body for a very long time, so you'll get a large dose of radiation. D cannot escape, sorry, not D, B cannot escape, so you'll get a high dose of radiation, and that's going to give you a much increased risk of cancer. But the benefits, D, overall, the benefits of treating your disease outweigh the small additional risk of the radiation. Why is it only a small risk? Because it decays relatively quickly. Alright, because after a day almost all of it will be gone. And on top of that, most of it passes out of the body. Right, because it needs lead to stop it, so actually your body will not do a very good job of absorbing this, and most of it will escape. So I think we've done everything. We've talked about the risks, talked about the benefits, we've linked it to the isotopes, we've linked it to the properties in this table. That should be sufficient for 6 marks. Okay, question 5. So there's a couple of really easy parts in here, but is worth answering nonetheless. So we've got Alex cycling up a hill. The mass of him and his bicycle is 95 kilograms. As he goes up the hill, GPE increases, so that's gravitational potential energy. We've been given the formula for it here. If they don't give you the formula, look on the data sheet. All right, I'm going to write this down. Look on data sheet, because you get the formulas this year. And then it says at the top of the hill, the gravitational potential energy store is 7,600 joules. Calculate the height at the top of the hill. So this equation I'm going to write out in symbol form, mgh, emgh. I'm going to rearrange for h, so I'm going to make h a subject. So I'm going to divide through by m and g to get h is e over mg. Then I'm going to substitute in my numbers, 7,600, mass is 95, and g is 10. Now you are expected to remember this, but here they've been nice to you and they've given you it. Sometimes you see g as 9.8, but obviously that rounds to 10, which is why we usually use 10 at GCSE. So plug this in your calculator and you get 8 meters. Okay, Alex transfers 9,000 joules to reach the top of the hill. Explain why the amount of energy transferred by Alex is different to the increase in gravitational potential energy store, which, as we just saw, was 7,600. So, why is there a difference? So Alex wastes some energy as heat in his muscles because they are not 100% efficient. Nothing is 100% efficient, so there's always some wasted thermal energy. And also, Alex does work against friction in the pedals and against air resistance as he cycles. So doing work means transferring energy. So this also means transferring energy, just another way of saying it. And again, where does this end up? This ends up heating the surroundings. So as we do work against friction in the pedals, it's like doing this, heats up the pedals. As he does work against air resistance, he's pushing the air out of the way and ultimately heating that up. Okay, part 3, calculate the efficiency of Alex to get to the top of the hill. So efficiency is useful energy over total energy. And if you're ever unsure, look on the formula sheet. Now you can also say that efficiency is useful power over total power. That is another way that you can say what efficiency is, and that is often used when we're talking about transformers, but here we don't need to use power. So the useful energy, well, we're transferring energy into the gravitational potential energy store, so the useful energy is 7,600. The total energy is what he transferred, so 9,000. So type that into your calculator. 7,600 divided by 9,000 gives you 0.84. Now that is fine as an answer. They haven't said how they want the answer. If you wanted to, you could do 0.84 times 100 is 84%. Sometimes they'll have an answer line with a percentage sign, but if they don't, this is absolutely fine. If you ever get an answer greater than 1, you've made a mistake. Do the calculation again. Okay, B, calculate the maximum speed Alex can reach when he goes back down the hill without pedalling. Assume no energy is lost, so we're going to assume there's no air resistance, no friction. Give your answer to one decimal place. So what information do we have, because there's no equations given? So we have the amount of energy that is transferred, so that is going to be the GPE going into the movement energy, which is kinetic energy. So that might give us a clue what equation we want. We have his mass, we're trying to find the velocity, and that should give us the information we need, which is the kinetic energy equation. Energy is half times mass times velocity squared. So the kinetic energy is 7,600, because that's the gravitational potential energy you started with that transfers to kinetic. That's half times mass, which was 95, times v squared. So you might be confident rearranging this really quickly. If you're not, I'll do it in 2 steps. So we'll do a half times 95, which is 47.5, times v squared. Then we're going to divide by 47.5 to make v squared the subject of the equation. So v squared is 160. And then finally v is the square root of 160, which is 12.6 to one decimal place, 12.6. Okay, part C. So this is 4 marks, so there's a good chance it's going to require 2 calculations if it's this many marks, or maybe some unit conversions. So it says Alex buys an electric bike which assists pedalling by supplying 11 amps of current from a 24-volt battery. It takes Alex 30 seconds to reach the top of the hill. A total of 9,000 joules of energy needs to be transferred by Alex and the battery to reach the top of the hill. Calculate the energy supplied by the battery and use this to calculate the energy that Alex needs to supply by pedalling. So we've got to calculate the energy supplied by the battery is 1, and use this to calculate the energy that Alex needs to supply by pedalling, which is 2. So there's immediately 2 steps, and if we carefully read the question, we see what those 2 steps are. So from the battery, we've got I, V and T. So how can that lead us to get the energy supplied by the battery? So what links I and V? Well, V equals IR is obviously 1, but we haven't got anything about resistance, so it can't be that one. We also know that power is current multiplied by potential difference, so we can immediately work out the power. Once we've got the power, we know that power, well, because we've got energy and time, power is the rate of transfer of energy, so energy divided by time. So we can easily get the energy. Energy is power times time. So if we do power times time, we can do energy is power times time, which is I times V times T. We can get the energy supplied by the battery. So this is 11 times 24 times 30. 11 times 24 times 30, which is 7920 joules. And that is part of the answer. That's the energy supplied by the battery. We need to use this to calculate the energy that Alex needs to supply by pedalling. So this is going to require a second step. So we need to use this second value here, a total of 9,000 joules of energy. So the total energy is the energy from Alex pedalling plus the energy from the battery. So 9,000 is the energy of Alex pedalling, which we're trying to work out, so we'll just call that A for E Alex, plus the energy from the battery, which is 7920. So then obviously if we subtract one from the other, this gives us the energy that we want, which is 1080 joules. Okay, part D. Alex says, if I cycle more slowly, I will use less power to reach the top of the hill. Explain why Alex is correct. So power is the rate of transfer of energy, or in simple form to make it really easy, power is energy over time. So if the time decreases, if this goes down and the energy stays the same, the power will also decrease. Oh, hang on a second, that doesn't make any sense, does it? I've made a really simple mistake and common mistake. If I cycle more slowly, that doesn't mean the time decreases, does it? If I cycle more slowly, it means if the time increases. It's so easy to make these mistakes. It's always worth checking your answers, rereading to avoid these silly mistakes. So if the time increases, so if this bottom bit of the fraction gets bigger, then the whole fraction gets smaller, so the power decreases. Now what have I also assumed? I've said that the energy stays the same. Is that correct? Well, it is correct. The energy stays the same because the height of the hill stays the same. Alright, the total GPE is always going to be the same because the total height of the hill stays the same. Now, if this was more than 3 marks, I might go into a bit more detail. I might even say if you cycle more slowly, less energy is wasted against the force of air resistance, because the force of air resistance is proportional to the speed you're going squared, but it's not more than 3 marks, so I don't think we need to get that complicated. Okay, question 6. So which ray diagram shows how rays of light are refracted by a convex lens? So refraction is when we have a change in optical density, we have a change in speed of a light wave. So if the density goes up, then the speed decreases. So we're going from air into glass, so the ray should slow down, and it should also bend towards the normal, which is the line at 90 degrees to the surface. So this one, absolute load of rubbish. This is reflection. So which one shows bending towards the normal? So what we would do is follow the light ray. We think about where it hits the surface. We put a ruler at 90 degrees to the surface at all of these points. This red line is the normal, and then we should be able to see whether it bends towards or away from the normal. So here the light ray is going straight through, but actually you can see it bends up, which is towards the normal, so it could be B. It also happens in C, it bends towards the normal, so it could be C. In D, well, it's bending the other way from the normal, so it cannot be D. So which one of C or B? Well, we need to do the same for when it comes out. We need to draw the new normal on. So the normal 90 degrees to the surface, it's curving the other way, so the normal will bend in the other direction. So now when it comes out, this way it's going this way and it's bending away from the normal. And this one, it comes out and it bends towards the normal. So we need to think, if the density now is going down, the speed is going to go up and it's going to bend away from the normal, which is B. Now, very often when you see these diagrams, we don't show them in this much detail. We literally just show them doing this to light rays. We just show them changing direction in the middle, which is obviously not what happens. It happens at the boundary. But this is often a simple diagram for lens diagrams. But this is all about refraction rather than just lenses. Okay, B, we've got blue light shining on a convex lens. So convex is the opposite shape. This is concave because it looks a bit like a cave. Convex is the opposite. So where convex spreads out the light rays, this focuses the light rays to a point. Complete the path of ray B. So that's really easy. It's going to mirror what happens to the top one. So you just need to draw it with arrows, doing what the top one does. You probably should use a ruler just to get a rough idea, but if you notice, this distance here is not the same as this distance here. So they are trying to catch you out a little bit, whereas if you just measured this distance, it would be down here. If you measured this distance, it would be down here. So they are trying to catch you out a little bit. Okay, ray A enters the lens at point X and leaves the lens at point Y. Explain why ray A changes direction at the points X and Y. Well, we've sort of already done it here, haven't we? So instead of copying it out again, I'll just run you through it. There is a change in optical density as the light ray goes from air into glass into air. Therefore, there'll be a change in speed. At point X, the density increases, the speed decreases, the light ray bends towards the normal. At point Y, the density decreases as it goes back into air, the speed increases, it bends away from the normal. And then part C, red light has a longer wavelength than blue light. Explain how the path of ray A will be different if red light was used. So red light has a longer wavelength, so it refracts or bends less than blue light. Okay, so if you think about a rainbow, you have red, orange, yellow, green, blue, indigo, violet. Red bends the least, violet bends the most, and the amount of refraction, the amount of bending increases as you go from red to violet, and that's all because of the wavelength. So on this diagram, if we were to use, well, I've already drawn this one in red, so supposing I was doing blue now, if I was doing blue, blue would bend more, so it would look something like this. Okay, blue bends more than red light. Okay, question 7. Edwin Hubble studied the visible light spectrum of distant galaxies and compared them to the spectrum of our sun. So we've got the sun, we've got X, we've got galaxy Y, and we've got the visible light spectrum. So what are these diagrams? So we've got, these are the colours, and these are black bands. So these are emission spectra. So light is shining out from the sun, and certain elements will absorb certain wavelengths. So there are certain, I'm going to put in quotation marks, missing wavelengths, because there are certain elements that have absorbed these colours from the sun or from galaxy X or galaxy Y, and then we can use that to identify the elements in the atmosphere of the sun or between the galaxies and between Earth. And if we know what we're looking for, say for example if this corresponded to hydrogen, then we could make really good comparisons between the different galaxies. So Hubble used his observations to produce the graph shown in figure 7.2, and you can see that as the distance between the galaxy and Earth increases, the speed a galaxy moves away from the Earth also increases, and it's a straight line through the origin, which means they are directly proportional. The question says, explain how the evidence in figure 7.1 and 7.2 leads to the Big Bang model of the universe. So we need to think, why is the sun different from X and Y? So we can see there's 1, 2, 3, 4 bands, and you can see that these bands have been shifted this way, and you can see that they've been shifted from the short wavelength to the longer wavelength, which means they've been what we call redshifted, where the wavelength has increased. So we'll just summarize that before we carry on. So we can say galaxy X has been redshifted. So the light has shifted to the red, which is the longer wavelength end of the electromagnetic spectrum. What's happened to galaxy Y? Well, Y has also done that. It's been shifted, but you can see it's not been shifted as much. So you can say Y has also been redshifted, but not as much. What about the sun? Well, the sun isn't redshifted at all. The sun is in our galaxy. The sun is like the reference point. So the sun is not redshifted as it is in our galaxy. So we need to explain this a bit. So why does redshift happen? Redshift happens, well, it's called the Doppler effect, which I don't think we're going to write down in this answer, but it's called the Doppler effect. So as galaxies move away from us, the light waves get stretched. So this is just like when you have an ambulance moving away from you. You hear the sound of that ambulance, or the frequency of that ambulance appears to decrease, the pitch of it appears to get lower. If an ambulance is moving towards you, the pitch, the frequency of that appears to get higher. So as the source, if this is the source, it would normally be emitting light rays like this. If the source is moving away from you, the light rays appear to be stretched, and if the source was moving towards you, the light rays appear to get squashed. And the faster the movement, the more the redshift. So X has been shifted the most. X has the highest redshift. So must be moving away from us the fastest. Now, obviously there is blue shift. Blue shift is the opposite. If galaxies are moving towards us, the waves get squashed, get closer together, and they appear higher in frequency. So this is blue shift, this is red shift, and this is normal. We don't need to talk about blue shift. It's not happening in this question. Is there anything else we need to do? We're just going to read the question one more time and see if we've missed anything out. So hopefully you've spotted that we haven't really answered this question. We haven't mentioned the Big Bang once. So how does this lead to the Big Bang model? So this leads to the Big Bang model because Hubble showed all galaxies, well, I say all galaxies, almost all of them. There is one local galaxy, Andromeda, that's moving towards us, which is blue shift, but that's on a really small scale. Overall, all of the galaxies are moving away from us. So all galaxies are redshifted, which means all are moving away. And if they're all moving away from us, this means that if we went back in time, they must have come from a single point, right? We can obviously put them back into one point. So they must have come from a single point close together, which is the Big Bang model. Okay, so we've now answered the actual question, and we've also explained what the graph and what these diagrams show us. Okay, question 9 on here, I'm going to let you do yourself. We're going to skip to question 10, which is this one on exoplanets. So it says exoplanets are planets that orbit stars outside our solar system. The table shows details on some exoplanets that could sustain life. So we've got exoplanet, we've got the star they orbit, we've got the mass of this star. So these two are linked. The orbital period of the planet. We've got the orbital radius again of the planet and the orbital velocity again of the planet. So this is to do with the star, and these three are to do with the planet. So I think that's just quite important just to highlight so we don't make any silly mistakes. The force needed to keep an object moving in a circle depends on the speed of the orbit and the radius of the circle. The greater the speed and or the smaller the radius, the greater the force needed. So this tells us everything we need to know for the rest of the question. Now, these are related with this equation, which you don't need to be able to use, but actually the force needed to keep something moving in a circle depends on the speed, the velocity of the object, the radius of the circle. It also depends on the mass of the planet. But this, like I said, is not actually needed. It's just putting this into an equation. So explain why Gliese, I'm not sure how you say that, 667 has a higher orbital velocity than Kepler 452b. Use the idea that the weight of an object is proportional to its mass. So weight is proportional to mass, or specifically weight equals mass times gravitational field strength. And this weight is a force. So let's look at the table. So this has a higher orbital velocity than Kepler. The radius is the same. The period obviously is different, because if it's going faster, then it must orbit significantly more quickly, so the orbital will go down. So I don't think we actually need this column. I think that's just sort of there to confuse us at the moment. And then what else is different? The mass of the star. So the radius is the same for both planets. That's really important, because what we're saying, this is the same, so we only need to consider force and the orbital velocity. And again, I'm pointing to this, but actually you've got it in this text here, so you don't need this at all. So the radius is the same for both planets, but what is different? The mass of the star Gliese is higher than Kepler, so its gravitational field strength is higher, and that must be true because the radius is the same. If the radius was different, then this would change, but we're not changing that. So the gravitational field strength is higher, so the weight, i.e. the force of gravity on the planet, so the weight on Gliese 667c is higher than Kepler 452b. Therefore, the weight is higher, which means the orbital velocity must be higher. So, as the force is higher on the planet is higher, its orbital velocity must be higher. Okay, so we've got that here, haven't we? The greater the force needed, the greater the speed. And the radius, the radius is the same, so that's not important. The greater the speed, the greater the force needed. Okay, so all the information is given, we're just putting it into a logical argument. Okay, B. Another exoplanet is discovered in orbit around a star. The star has the same mass as Kepler 452, so it's this same mass here. The orbital velocity of the planet is about the same as Earth's orbital velocity, so the orbital velocity is smaller than this. What is the possible range of values for the orbital radius of the exoplanet? So what we really need to do, we've got this is the mass of the star, we've got this is the orbital velocity, and we want to know what the range of values is. So what's the biggest possible value it could have? Well, the biggest possible value it could have is this, because then it would match Kepler, and the smallest possible one it could have is probably this here, because then it would match Earth. It's probably in between, and it's probably higher than this, because obviously this mass is higher, so we wouldn't expect it to be so low. So it's probably between 150 and 225 times 10 to the 9 meters. So we need to explain this. So the orbital radius must be greater because the mass of the star is greater. So that's kind of what we explained in the previous question, didn't we? The greater the force needed, the smaller the radius. Hang on, have I said that wrong? No, I haven't made a mistake, although it sounds like I've said the opposite of this, because what else has changed? The orbital velocity has decreased. So this is importantly, and the orbital velocity has increased. So both of those things are true together. So if you're struggling to kind of understand what I've said, think about having a tennis ball on a string, all right, and you are there whirling it round. If you increase the mass of you, and if I increase your mass, what I'm really doing is increasing the force that you're pulling with, I'm increasing the weight effectively, then I'm going to be pulling this tennis ball faster, which means I'm going to speed up the rotation of this tennis ball. But we know that the actual velocity of the planet, of this tennis ball, has gone down. So how do you, if you're pulling this tennis ball, spinning it around in a circle with more force, how do you make this actually go more slowly? Well, what you must do is you must make the string that it's on longer, so it's further away from you. So now you can pull with more force, but it will actually be going more slowly because the radius has increased, which is what we said right at the start. So I picked this question because it is quite tricky. I would encourage you to really think this analogy through if you're struggling, or even when you get home or you get into PE or something, you can demonstrate this. Get your keys on a piece of string or tennis ball on a piece of string, and you can try this out and you'll see exactly what I mean. Okay, we're going to do one final question. So we're going to do question 4 about waves. So different types of waves can be used for communications. 50 years ago, microwaves were used for long distance communications. Microwaves travel through the air between microwave aerials. Now, light waves travelling along optical fibres are normally used instead. Compare and contrast microwaves and light waves. So compare in this case means the same, contrast means difference. Now compare could mean give the differences as well, because they've specifically said contrast, we know it's similarities and differences. So what is the same about both of them? Well, they are both EM waves, which is electromagnetic waves. They both are therefore transverse waves. They both travel at 3 times 10 to the 8 meters per second in a vacuum. And they obviously both can travel in a vacuum because they're both electromagnetic waves. What is different about them? Light, compared to microwaves, has a higher frequency, a higher energy, and a smaller wavelength. Now clearly you don't need to write all of that for 2 marks, but that's lots and lots of differences. So we now need to calculate the speed of light waves in an optical fibre. Use the data sheet. So this question, deceptively hard. So what information have we been given? We've been given the speed, we've been given the time, and if we read this really carefully, time to travel 90 kilometers. So we've also been given a distance. So what relates these 3 things? Obviously speed equals distance over time, but we've still got to make sure we don't make any silly mistakes. So the speed we're trying to work out, the distance is 90 kilometers, and the time to travel is given as 450, but we have to look really carefully, microseconds. So this is 90 times 10 to the 3, and this is 450 times 10 to the minus 6. So just as a quick recap, we've got micro, which is 10 to the minus 6. We've got milli, which is 10 to the minus 3. We've got nano, which is 10 to the minus 9. We've got kilo, which is 10 to the 3. We've got mega, so capital M, which is 10 to the 6. We've got giga, which is 10 to the 9. And we've got tera, which is 10 to the 12. If you're in chemistry, you've also got deci, which is 10 to the 2, and you've also got C, which is centi, which is 10 to the minus 2, which obviously do get used, but we often don't see them in these tables where it's these prefixes where it's thousands. So easy to catch us out. Now if we put this in our calculator, when I do this, I'm going to use the fraction button just so I don't make any mistakes with my prefixes. So times 10 to the minus 6. This way there's very little danger of you doing it wrong. Lots of zeros here. It makes sense to give this in standard form, 2 times 10 to the 8. If you ever get an answer that is bigger than 3 times 10 to the 8, you are wrong, because you can never have anything travelling faster than the speed of light. Okay, the next part of this question is here. So an engineer suggests using an optical fibre made using a new material. In this new material, light waves take 432 microseconds to travel 90 kilometres. Calculate the percentage decrease. So you often do this when you're looking at biology practicals like osmosis, or maybe chemistry practicals if you're looking at the mass change in a reaction. So the percentage decrease is the change over the original. So we've got 450 minus 432 divided by 450, which is 18 over 450. 18 divided by 450, which is 4%. So obviously I need to times this by 100 to get my percentage. So it says the new material will be 10% more expensive than the old material. Why is it not worth using this material? Use your answer to part B, I. So it is 10% more expensive, but only gives a 4% saving. So it's 2.5 times more expensive than the saving. So it's just not really a sensible decision. So we're going to finish the walkthrough there. There are plenty more questions in this pack for you to practice independently. Most of them cover similar things, and there's a couple of other ones in there as well, but you will obviously be provided with the answers to all of these.